Good. So let's get started. I hope everybody is able to join in the chat, and otherwise perhaps some will still jump in. My name is Caroline, and it is my great pleasure to welcome you today to the session on disruptive tech for Africa. So first, I'd like to start with a few housekeeping rules. First of all, I'd like to let you know that there is a live translation to French available for this session. You can find it at the bottom of your screen. For Zoom meetings, you'll see kind of a globe with the word interpretation below. If you click on that, then you can go to another breakout room where you will get the audio in French, but you will still be able to see the same screen as we are seeing in the English room. Second of all, I would like to mention that the session is being recorded, so please be aware of that. And also, as the speakers are giving their presentations, we will try to keep all of the questions for the end. So please write any questions you might have in the chat, and we will have a general Q&A session at the end of this session today. So what is this session going to be about? We see that urbanization is changing Africa, is changing the face of the continent. Africa is urbanizing incredibly rapidly. If you look at the share of urban population compared to the total population in Africa, it is really growing significantly over the past few years. And a lot of this growth is happening in a manner that is unplanned and informal, making it very difficult to plan adequate services. And a lot of the population growth is actually happening in vulnerable areas. And understanding this growth and where this growth is happening resonates very clearly with the theme of this conference, which is understanding risk in Africa. So this session is going to be all about how new disruptive technologies can actually help understand the risk specifically for Africa. We are going to be talking about brand new data sets on urbanization that are from satellite images that are going to help track urbanization across the continent in many different ways. We're also going to talk about how to validate these large machine learning models that are now emerging. So for example, how can we include street view imagery to incorporate knowledge from the ground? And also, how can we validate them using local knowledge? How can we really include the skill development of the local population through microtasking, which enables us to both create employment opportunities locally, as well as validate the data sets using local knowledge. So for the session today, we will have a number of very interesting speakers lined up. First of all, we will have DLR, the German Space Agency, who will present on the World Settlement Footprint, a suite of products that is brand new and should be released early next year. So we'll give you a sneak peek on that. Then we will have a presentation from Mind Earth on how to use street view imagery. We will have a short video showing the microtasking work that has been done a few months ago. And we will have Dr. Zakaria from Aida University and the Resilience Academy presenting on what it meant for the students and the workers in Tanzania. After that, as I mentioned before, we will have a Q&A session where we very much look forward to your questions. So without further ado, I'd like to hand it over to Mattia and Thomas from DLI to start with the first presentation.
I think you have to unmute, Mattia.
Okay, sorry. Okay, so we should be there in a second. You see the screen, right? I hope so. Yeah.
Yes.
So thanks a lot, Caroline, for the introduction, and thanks a lot for you all. I mean, as you can see from the title, I mean, we're dealing about monitoring global urbanization with bigger data, and specifically, we will introduce a suite of new products, the World Settlement Footprint, of which we will give a specific example to Africa as it's the goal of this session. And first, let me just start with acknowledging the support from the initiative of the African Caribbean Pacific Group, specifically the Natural Disaster Risk Reduction Program that has been funded by the European Union and managed by GFDRR, has been supported the big part of the slides of the work that we're going to present. So yeah, we know that urbanization happens, and sometimes it has gone a bit crazy, as you can see here, but also as in this example referring to Cairo, for instance. And we know that monitoring globally is extremely important for a variety of applications that involves the human presence. So just to cite some: risk assessment, epidemiology, socioeconomic development, population distribution, etc. And so at the German Aerospace Center, DLR, we have recently launched this suite of novel products, the World Settlement Footprint, which are open and free. They have a high spatial resolution, and especially they are global. And we derive information not only related to the current and past extent of human settlement, but we try to go on and provide some additional information, for instance, about the percentage of impervious surface, building height, or even the population distribution. And let's say that these layers are actually currently being employed and further developed and improved in the framework of the Earth Observation for Monitoring Urbanization in Africa, a project that has been directly supported by the World Bank with the goal to further improve these updates and to regularly update them specifically for Africa, but also to assess their capability to really track the urbanization at high resolution and high time frequency for the whole continent. So the first product that we have been working on dates a couple of years back, namely, it's called WSF 2015, and it's a 10-meter resolution binary mask which outlines the settlement extent, as it says the name, for the year 2015. And we did this by jointly exploiting for the first time both radar and optical satellite data. Specifically, we used Landsat 8 and Sentinel-1 imagery. And we can say that currently that's the most accurate existing global layer of its kind. And this has been assessed based on a huge validation exercise performed through crowdsourcing information that has been supported at the time by Google, where we could label about 1 million of validation samples. And to give you an idea, here you can see really some examples at different scales. But let's say the common term is that besides the major cities, the layer with respect to all the others that have been produced up to that time allows a very good characterization also of the suburban and the rural areas, where still we have to remember that half of the global population is living. And to give you, say, an example more in detail, we can see here an area referring to Nigeria. And actually, you can see here now how the layer performs there. So pretty good. And even in this challenging situation, it could really identify the continuum of villages in the specific target area. But of course, we're talking about 2015. Now, what we have been doing is to start producing, and we are almost there, the new layer, so the WSF 2019, where we substituted Landsat 8 with another satellite, Sentinel-2, whose resolution this time is 10 meters. So in the example here on the left, you can see an area referring to Nairobi at 30-meter resolution as it was before. And now that we're moving to Sentinel-2, you can see the corresponding area with 10-meter resolution. And of course, that dramatically changes, and it allows, let's say, an unprecedented detail, as you can see in this example. So here we reported let's say, some figures about the city of Monrovia in Liberia. And this was our previous layer, which we can say performed rather good. But now that we have this improved detail, we can aim at something like this. So really, we can really go down at a very precise mapping, sometimes even at the building level. So we can have a look into the zoom, and you can see that here, this is actually how it performs. So I flicker a bit, but I guess that you agree with me that the product performs particularly well. And if we superimpose the 2015 layer masked with this new layer, we could have already an idea of where the most of the urbanization occurred in the last 4 years. Another example here refers to Nairobi, and here it's how it looks previously and how it looks now. So again, it was already good, but now it's even better. And we can see, especially in this case, that the city developed quite considerably towards northeast and east. And the last example referring to Lusaka, so the capital of Zambia. And this is how it looked for the 2015 layer and how it looks now, because now we really have the capability of taking away, for instance, all the remaining green areas that previously, due to the fact that 30 meters data were used, were, let's say, unfortunately still characterized as a settlement. But we don't want to stop there, because what we want is not just to provide, let's say, a binary information of a pixel, if it's a settlement or no settlement. We really would like to go over and let's say the first information that we are adding is that about the percent impervious surface. So in general, this information is a good proxy for the building density, and it's of key support in several applications like better distribution in the population and urban models, or assessing the risk of urban floods, or characterizing the urban Italian phenomenon, because let's say imperviousness really refers to the capability of letting, let's say, the water not penetrating. So what we did here was to generate this new layer, the WSF 2019 imperviousness, which still has a 10-meter resolution and estimates the percent impervious surface for each pixel that we marked as settlement in the original binary layer. And to do this, actually, we exploit the correlation that exists between the normalized different vegetation index and the percentage impervious surface. So let's have a look to this example referring to Kinshasa. And this is how it looks in the binary layer. But now, if we add this impervious information, you can see that we already have at this stage a better idea of what's the urban form, what's actually the morphology there a bit of the city, because the red areas here actually really corresponds to where you have a higher density with respect to the ones in yellow and especially in green, where you have let's say a lower density and a higher presence of green areas still. Another nice example refers to Lagos, and you can see how impervious, actually, how dense the city is, especially in the southern part. But as we move to north, where most of the urbanization is actually occurring in the last years, we still see that there, let's say, the density is not as much as in the main body of the city. And as a last example here, we take Harare in Zimbabwe. And with respect to the other two examples, we can see that here we have a greener city, as it's say testified by the presence, let's say, of quite many pixels in light green tones. But again, we want to do even better, and we actually would like also to provide an overlayer where we reliably estimate the population density. And this is, you know, really important for several applications, and to really allow an efficient government policy, you know, to understand where there's more need for intervention planning, or to understand where there are people at risk. So here we used, say, as an idea, we took the WSF 2019 imperviousness, and we use this as proxy for distributing people, because as I mentioned before, in general, it performs well as a proxy for the, you know, the building density. And then we came up with this new layer, the WSF 2019 population, which estimates per pixel the number of inhabitants. And we can see a couple of examples in the next slides. So what we had at hand were the population figures for these administrative units. And what we did was to redistribute these figures in the corresponding area according to the imperviousness. So you see, this is an example referring to Kampala in Uganda. And this is actually what we could obtain. So we see that, for instance, all Kampala in the center is characterized by, for instance, a lower density with respect to the, say, areas at the neither top and bottom. But as soon as we fade out, let's say we move out to the city, just where you have, let's say, a bigger cluster of smaller settlements tend to correspond to a higher number of inhabitants, whereas, you know, as you approach the rural areas, the density goes particularly low. And another example here in Cape Town, where we had at hand way more granular information at the administrative unit, you can see that the final product looks like this. And actually, it's quite interesting because in this case, we really have, let's say, polygons corresponding to the industrial sites where no people are living, and these are correctly associated, for instance, with the white color corresponding to no population. But I mean, this refers to the current status. We want also to understand what occurred before in order to better plan for the future. And so that's why we also look backwards and we started generating the so-called WSF evolution products. And here, the first idea was, let's say, to outline the growth of the settlement globally at 30-meter resolution on a yearly basis from 1985 to 2015. And this has been generated with the strong support of the Google Earth Engine team. And there we processed the entire Landsat 5.7 archive that included more than 7 million scenes. And here, let's say, the hypothesis is that we start from our mask, referring to the year 2015, and then we check for each pixel if a breakpoint occurred previously. And so in this way, we just consider settlement growth. We don't consider, let's say, settlement shrinking, but let's say at the global level, statistically, we do believe that, you know, this might hold in 99.9% of the cases. And I hope that you can see the animation fluidly. Here you can appreciate the estimated settlement extent growth for Cairo in this 3 decades. And one can really appreciate how first the city tend to expand more toward the eastern part, but then also to the west. And we can also see this with colors. So in the static representation, so you see, say, more green and yellow pixels, especially, let's say, in the right part of the figure, meaning that the big portion or the big part of, let's say, urbanization occurred in the years 2000. But then a lot of blue also, especially in the western side. And then another example which testifies a completely different pattern of urbanization here is the example of Dar es Salaam. So the city, let's say, grows by basically eating and incorporating the suburban areas. And one can also appreciate this with the colors that has a kind of a shading from red to blue and violet, eastern to east to west. And yeah, and here you can see some other example just to give you an idea of how good the product is and how different pattern of urbanization you find. For instance, above you can see Cape Town and Abidjan, where actually the urbanization occurred in a more blocky and patchy way. Especially in the case of Cape Town, this could really be due to a proper management and a sound master plan behind. With respect, for instance, to Kampala and Nairobi, where, let's say, you have the idea that urbanization mostly occurred informally and without such a clear master plan as in the example above. But also we have to say that since this product is based on Landsat data, actually, unfortunately, the availability of data was not always as good as today. And so to take this into account and to make the users aware of this, we conceived a score, the so-called input data consistency score, which characterizes the goodness of the input Landsat imagery for each of the years. And here you can see the status for 2015, where in general, actually it was particularly good more or less everywhere in the world. But if we go back, for instance, to the year 2000, we can definitely see that in Siberia, and especially in Western and Central Africa, we had quite some vast regions with very low data availability. So this translates in lower quality of the product that, of course, does not really depend on the methodology, but rather, unfortunately, to the poor availability of the data. But once we have this data, actually, we can really start doing something that previously was not possible. So we can really track how this settlement extent growth occurred in this 31 years. So we see on the left the case of Egypt, which seems particularly good, but on the right, we see the case of Gambia. And honestly, there are some discontinuities that do not really like reasonable. So what we have been doing here is to first, let's say, associate each of the points with the average IDC score for the specific year. And we noticed that while the data availability for Egypt on the left were mostly very good, in the case of Gambia, before the year 2000, I mean, we didn't have much data. That's why, of course, as I said before, the performances are not as good as one would expect. So to cope with this, we apply some cutting edge technology, and we, let's say, use the empirical supervector regression, which is weighted based on the IDC score. So taking into account that where you have better data, you have higher reliability, this is actually what we could model. So you can see that in the case of Egypt at the left, it's more or less going through all the points. But in the case of Gambia, it really seems reconstructing what is actually occurred. And then once we have this, we can do several more analyses. Here, for instance, at the bottom, you can see the corresponding yearly settlement extent growth, which gives an idea of how fast actually the urbanization has occurred. But something more can be done, and I find this animation quite enlightening. Let me guide through that. So here you can see different circles corresponding to the different countries in Africa, and the color corresponds to the macro region, the UN macro region where they belong to, and the size of the circle is proportional to the population. So in the x-axis, we have the percent growth of the population with respect to 1985, while in the y-axis, we have the percent growth of the settlement extent. So if now I put this line is the equal percent growth. So saying, okay, if 1 point lies there, it means that the proportion, the percentage growth of the population equals the percentage growth of the settlement extent. And actually, you can see that for the very most of the country, they lie, let's say, at the bottom part. This means that in the vast majority of the cases in Africa, we experience a densification because we have a higher population growth with respect to the corresponding settlement extent. And here I would like to draw your attention specifically to the circles in orange, which correspond to the Middle African countries. You can really see that here we have a population growth even up to 160% in front of a settlement extent growth of just 40%. So this is actually quite remarkable. It means that really the densification there was massive. Compare, for instance, to the the dots, the circles of Northern Africa and Southern Africa that are more clustered, towards too close to the equal percent growth. And then, I mean, I go on because I know that I'm running already a bit out of time. So just to give you an idea that what we want to do and we are working on at the moment is really also to provide an imperviousness version of the evolution. So actually to give the possibility of understanding how the densification of the cities has occurred. And here you can see an example of Johannesburg, and you can appreciate, for instance, these townships in the outskirts of the city that's getting more red, meaning more dense. And this is exactly where most of the Black people have been evicted from the city center, for instance. So there's also a social component. And as well, we would like also then to come up with a WCF evolution population. So where really we have for each of the 31 years globally, let's say an estimate of the population density. And now I leave the floor to Thomas, who will guide you through the WCF 3D.
Yes, thank you, Mattia. So one of the, let's say, latest products that we are working on is also primarily actually aiming at supporting the population modeling or the modeling of the population distribution by means of providing a more accurate description of the, let's say, build-up density. And we all know that ideally to do so, one needs also information about the build-up height. So that's why, let's say, using the WSF 15 at the current stage as a building mask, a settlement mask, we now use also 3D information provided by the Tandem X digital elevation model, which was derived based on data from the German Tandem X mission. And we use this height data to estimate, let's say, the local build-up heights for all settlements, actually globally, and at a given spatial resolution of 12 meters. And we have this limitation of the 12 meter because the Tandem X height model, which is available globally, has this spatial resolution or geometric resolution. Of course, I cannot go into details. So if you're interested in the methodology behind it, I refer to this link. So it's a recent publication where we describe the methodology. As you can see here, basically from the data, it's of course kind of a multi-source approach. Of course, primarily we use the DEM, but also we integrate radar information, also OpenStreetMap data, for instance, on the location and outlines of buildings, but also Sentinel-2, and as I already mentioned, the settlement mask of the WSF-15. We also currently perform a validation campaign, which was based on crowdsourcing labeling, and this will be introduced by our colleague Davide from Minders later on in this session. So just to show you some examples of first results, let's say, here's an example of Dar es Salaam, how it looks like in the usual optical domain. Now we see here coming the 12-meter height or elevation model. So there in, let's say, the bright colors means at the higher height above sea level, in this case up to about 180 meters or 120 meters, mostly what you see. And of course, you see Dar es Salaam on the right-hand side at the coast. You already see some local structuring of the houses, etc. So in the next stage, based on this, of course, we then estimate in our example on a 90-meter first spatial resolution, the local heights above ground. So also there are specific reasons why we first go for the 90 meters. I don't want to go into details here. One of the reasons is actually also to minimize local errors. And since we have kind of a normal distribution of the errors, by this we can finally increase a bit the accuracy of the estimation. So what we can then at the moment already provide is actually at the African-wide scale, the first 90-meter product. And now here you see just another visualization example. For instance, if you have this typical 3D visualization. Also, we currently work on different kind of definitions or parameters regarding the height that we provide at the 90 meters. What I showed you just before was the average height within a 90-meter cell. We can also provide the average building height. So it's a difference. It depends also on the number of buildings within the cell for these 90 meters grids. And we can also, for instance, describe the basic floor space, let's say, which is a function of the building footprints multiplied by the average height, and assuming, for instance, a height of 3 meters per floor. So these are at the moment different stages that we're working on. And also, finally, we even want to go down, which you can see in the next image as an example from the center, city center from Dar es Salaam, to the building levels. So you might know, for instance, from different campaigns, also OpenStreetMap, for many cities, actually, we have a very good and accurate description of the building outlines. And now we are actually or currently working on also estimating precise heights for these building outlines. And with this, of course, you can imagine one takes this as an input for the population distribution, and we can assume that this again gives an additional, let's say, improvement in terms of the accuracy that we can achieve. Also then, just as a final slide here, to give you an indication that we work on the validation. Of course, we currently then compare this to reference data and that has been collected and is available in order to have a precise idea of how accurate this estimation is. Of course, and again, you can all find these informations in the paper that I initially mentioned. What we see at the moment is that it's comparably accurate up to 3 to 4 floors. If you go to very high buildings, we get an increasing estimation error of the height. Okay. So just then finally 2 other additional slides, which are just artist views, let's say, of the height data that we, as I mentioned, have already derived for entire Africa. Here's Nairobi. On the next slide, it's an example of Cairo again.
Sorry to
finally,
interrupt, Thomas, but could you keep it to 1 or 2 sentences more? Sorry to round up, but we have other speakers also who are waiting to present.
Yes, so it's the final slide, the next one. Just finally to mention, we are also working at the moment on a web application where all this information layers that you have currently seen will be presented and can be analyzed and even downloaded in the future. So that's our, let's say, instrument to make this data really accessible and also allow you to analyze it even online. So that's this example here. Thank you.
And just the last milestones, the WSF-215 is there. The tuna and can be assessed on Figshare, this repository connected to nature scientific data. The WSF-2019 and the imperviousness, we are refining the processing, but the post-processing, but they will be there in a couple of months. And the population maybe in half of next year. And WSF evolution, we are validating that. We expect that in Q1 2021. And as Thomas said, the WSAT3D has been completed for Africa. We expect to release it globally around Q1, Q2 next year. Thanks a lot for your attention.
Thank you. And again, if there at the bottom of the screen, you can see the emails of Matthias and Thomas. So if you have any more questions, you can also ask them. And with that, I would like to ask David from Mind Earth to give the next presentation on Street View imagery. And also, David, please pay attention to the time as we are presenting.
Thank you a lot for your introduction. I will share my screen now. Can you see my screen?
Yes.
Yes.
Okay, great. So in this presentation, I would like to discuss how Street View surveys can be used to improve our modeling of African cities and also to gather precious information on risk exposure and in these vulnerable areas. So, but first of all, what are Street View surveys? So the idea is that we go in a certain neighborhood or city and we acquire 360 degrees images of every road of the town or the neighborhood in a dense way. So every 2 or 3 meters, we try to have 360-degree pictures. And these databases basically constitute a snapshot of the status of a certain area at a given moment of time. And these are basically accessible and are ready to be explored later on. And why do we do this? Is that because once we start to collect dense pictures from the ground, we have access to a wide amount of other information that are not seen from the air or from satellite or aerial surveys. For example, here we see a picture of a building, and from the Street View image, we can clearly understand that this is a school, and so that probably nobody's living there. Also, we can add other informations that can be identified from the picture. For example, the road is sandy, so there is not paved, and there is no kind of a drainage infrastructure visible in this picture. And this kind of information actually cannot be easily inferred from aerial surveys or from satellite imagery, even if we had precise building outlines of the buildings. And otherwise, this information is very difficult to gather because it would require to have people going door to door to survey the land use or the number of people living in a building. The important aspect of the Street View surveys is that they are typically run involving with a deep connection with the local communities. So the idea is that local people with proper equipment would go and perform the surveys once they have been specifically trained. And this is because their knowledge of the streets and also the fact that they are known in the neighborhoods would allow to gather this information without disturbing the local population. And here you see some pictures of previous surveying campaigns that we ran in Brazzaville and Pointe-Noire in Republic of Congo. And this kind of activities actually strengthen the knowledge of the people in the process of collecting precious geodata and understanding the conditions of their towns. Actually, after you have collected all these images, what you can do is that you can process with semi-automated or automated pipelines these databases to extract precise geographical information that can be useful for supporting development programs and helping us understand the evolution of and the conditions of the town. For example, one can map economic activities, can determine what is the use of each building, the height in terms of number of floors, and the conditions. For example, if it's under construction or destroyed, or if it is in good conditions. We can also map the drainage infrastructure. We can, in certain cases, explore visually if the drainage infrastructure is stuck or damaged. And we can create maps of the road surface and conditions. And this can be done after the surveys, so at any given moment after we have run the survey, we can go back to the images and perform other classification or modeling tasks without having to go back to the field. So Mindart has created a proprietary technology to collect a huge amount of pictures in a participative way, employing local population in several countries in Africa. This technology is basically composed of a surveying backpack or acquisition unit, which basically is connected to a camera and a GPS receiver, and is holding batteries to perform 8 hours of surveys continuously without having to charge. And this system can be installed on a backpack and easily carried around the roads. But if the roads are sufficiently large, it can be also installed on a vehicle with a tripod, as it's seen in the center of the slide. Also, we have developed a complete visualization platform that would allow us to explore the images later on, and also a pipeline to perform geoinformation extraction from the images. And I will give you some examples in the following. This technology has been applied already in collaboration with the World Bank in Abidjan, Kinshasa, Brazzaville, and Pointe Noire, surveying several neighborhoods and acquiring hundreds of thousands of images in the last 2 years. These are some of the results that we are actually producing. For example, we are employing machine learning to automatically detect what are the informal economic activities that are on the road. And we can create actually precise maps of where the economic activity is running in a city. You see, for example, here the neighborhood of Matete in Kinshasa. And you see that the regions where people tend to gather to sell or to do business are clearly visible in red. And 2 examples of the roads are shown in the bottom. You see that in the left, we have just a couple of activities of stands, whereas in the right, it's everything is very packed and crowded. Also, we have developed a platform to do building classification and building use, so that this can be used participative as it works in OpenStreetMap, and the buildings can be associated with a class and with the actual economic activity that is being run inside the building. And this would create exactly the information that is very difficult to determine from aerial surveys, because we don't have the resolution and we don't have the access to the features on the facades of the buildings. Last but not the least, we also used this methodology to gather validation data for other remote sensing products. And for example, Thomas was mentioning the WSF 3D before. So we used millions of street view imagery that was available from Mindart campaigns or from Pillary data to ask several students in Tanzania to tell us what is the height of the buildings that they see in the pictures. And this is basically creating high accuracy geodata to validate the WSF 3D product, as will be discussed later in a dedicated presentation. Thank you for the attention. I leave you with a picture from Brazzaville, where we can see one of the successful development programs of the World Bank renovating the neighborhood that has been recently documented by Mindart with the Street View survey. Thanks a lot.
Good. Thank you very much for this nice presentation, David. In the interest of time, I will skip the video for now, also because I noticed that some of the animations are not going very quickly, at least to my connection. So I would like to invite Zakaria, Dr. Zakaria from Ida University, to start his presentation about the microtasking. So now that we have seen what it was from a more technical point of view to collect the data of the satellite imagery and from the street, we would like to go to Tanzania, where we will hear from the local perspective what it was like. Zakaria, can you hear us? Or me? No?
Do you hear me?
Yes, now I can.
Okay, I'm sharing my screen.
I cannot see it. I don't know if the other participants can. Could you perhaps try sharing your screen?
Yeah,
Ah, okay, now it is
I'm
set.
sharing the screen now.
Yes, perfect, thank you.
Yeah. I'm presenting about microtasking, which is part of the Resilience Academy project that was conducted at the University in collaboration with the University of Dar es Salaam and the other partner universities from Sokoine University of Agriculture and the State University of Zanzibar. Let me present about a Resilience Academy. What is it? A Resilience Academy is engaged to train young people, mostly students, with the tools and knowledge and the skills to address the world's most pressing urban challenges so that they can discover solutions for resilient urban development. And through the use of open tools, which are affordable and locally adaptable, tools and technology. So these students or the young people, they collaborate with the locals into the participatory mapping approaches to make learning widely accessible to the wide audience. So through Resilience Academy, this project also imparts and exposes students to geospatial data skills and the project management skills to map or unmapped areas and make community assets visible. So through the Resilience Academy digital skills, a number of areas are involved. Number one, climate risk database. We have also e-learning materials developed through Resilience Academy, and mass internship where students get an opportunity to practice and learn new skills on digital geospatial data. And finally, we have a component on research and innovation, especially to devise low-cost technologies for the benefit of the nation. Now, what about microtasking? The microtasking was a kind of a project where Research Academy partnered with the Mind Earth under the World Bank funding for micropayment project. Now, this project aimed at building local skills in order to create the required digital skills and the digital information knowledge, at the same time providing learning and livelihood opportunities for Tanzanian youth, especially those who are in higher learning institutions, universities. Again, the microtasking provided learning opportunities on valuable digital skills and geospatial technologies. So the youth who are involved were getting knowledge and the skills on digital geospatial by applying the tools locally made and openly available. How was this microtasking conducted? The Resilience Academy students from 4 Tanzanian universities, Aridh University, University of Dar es Salaam, Sokoine University of Agriculture, and the State University of Zanzibar, took part into the digital microtasking jobs. The job itself was about validation of satellite imagery, and this was the world footprints produced by the German Aerospace Agency and under the support of the World Bank. So there was a classification of the world settlement footprint in 2019. And this project was conducted online. Everything was online. So students used their smartphones, laptops, or even desktop to accomplish the microtasking. And after accomplishing the microtasking, the work of validating satellite imagery, there was a way of checking whether the student work was good or not. And finally, each student got paid using online mobile platforms available in Tanzania, the Tigo Pesa, Vodacom, M-Pesa, Airtel Money, and therefore this was how the microtasking was conducted. In a total of 200 students participated in the microtasking. This one was conducted here at Addis University. So Addis University and the State University of Zanzibar and the Sokoine University of Agriculture, in which 50 students from each of the participating university. So in total, 200 students. The microtasking was essentially a cash for digital work, providing sort of employment to youth to validate this data, world settlement footprint, three-dimensional world settlement footprint for future urban planning, but also for risk reduction. This kind of microtasking provided an employment opportunity for African youth. Yeah? In this case, it involved the university students who are future experts. We expect them to be future experts in the area of digital, geospatial, and therefore it was an opportunity for the Resilience Academy to provide the skills related to geospatial technology and the tools. So this all what took place on microtasking. Thank you.
Thank you very much for your presentation. I'll share my screen one moment. I would like to open the floor also to some questions from our audience first. Unfortunately, we only have time for one or two.
Sorry, should I stop sharing?
Yes, please.
Screen?
Thank you.
Okay.
I'll share the background side. I saw that there was one question already in the chat. And now that I'm sharing my screen, I seem to have lost my chat. Here we go, found it. There was a question for David. I don't know if you saw it already in the chat. Yes, so the question was, is there a way for public contribution to the Mind Earth project, and are any of your outputs, tools, or data open source?
Yeah, so up to now, the campaigns that we have run in Africa were supported by the World Bank and data as property of the World Bank. And we are now working on releasing the data on other crowd mapping platforms. And regarding to the public involvement, we are now working on extending the platforms that we have for classification to allow for crowd mapping of certain features of the environment, such as the building conditions and the building use, that could be like accessed by general users that would like to help to do this kind of classification tasks. The problem is that sometimes I mean, we already involve all the people that are interested in this kind of things via the local committee or local youth mappers organization. So those people are already contributing to our projects.
Okay. And so if anybody would like to contribute, I guess then they have to contact you directly.
Yeah.
Okay, good. Are there any other questions from the chat? Please feel free to ask them there. And as I mentioned before, on the screen that you are seeing now, you'll see the link to our forum. You can also write in any feedback or questions you might have that you're not able to ask right now in this session. And then I will make sure that they get to the right speaker. Okay. So as there are no questions, I guess at seeing the time, unfortunately, we will need to stop here and give you all time to go to the next one. So I will, on behalf of all this, first of all, I would like to thank all of the speakers for contributing today. I think it was very interesting to see the progress on all of your work. And also to the audience, thank you very much for joining us today. And please do again, let us know what you thought and any other questions you might have. Thank you.
Thank you as well.
Thank you, Caroline.
Yes, thanks a lot. Bye-bye.
Thank you very much. Bye-bye.